In this lesson, we're going to be looking at compositions of functions, which is when we apply the input, we take the input of one function as the output of a different function. So let's start by defining our composite function. So the composite function, and we're going to call this f composed with g, and we're going to use that little open circle to signify composed with. We're going to define that as f of g of x, where the input of the function f is the output of the function g. So we'll be taking an x value, we'll be applying g to it, getting some output, and then we will take f and we will apply f to what the output of the function g was. So let's look at, this can be a bit abstract when we're looking at it just as a general definition. Let's look at a few examples so we can see what that means when we're talking about actual functions. So, first example. Okay, let's take f of x equal x squared plus 1 and g of x equal 3x plus 1. Okay. First thing we're going to do is let's find f composed with g of 3. So what we're going to do is we're going to pick an actual input value for x, a actual number as opposed to a variable, and see what that comes out as. So f composed with g of 3 is the same as f of g of 3. So we're going to find g of 3 first, and then we're going to take f of that. So g of 3, we plug 3 in instead of x, so we get 3 times 3 plus 1, which gives us 10. So now we're going to find f of 10, and so f says we take x squared and add 1, so f of 10 is 10 squared plus 1, which is equal to 101. Remember, when we write f bracket 10, it's not f times 10, it's f of 10. That's the input to that function. Okay, so we've done it with a number for x. What if we just want to find the composition of the functions so that we can apply it to any number that we plug in for x? So, next question is find f composed with g of x for my same f and g. Okay, so remember that f of x is x squared plus 1, and g of x is 3x plus 1. Okay, so f composed with g of x, as we said last time, is equal to f of g of x. So we are going to find f of, well, g of x is 3x plus 1, so we're going to find f of 3x plus 1. The thing that can get a little bit confusing here is now we're going to take the 3x plus 1 and we are going to replace the x in our f function with 3x plus 1. So we're going to, and the reason it gets confusing is because you're now substituting an expression that contains x for an x. But all that means is that where we had we're taking this input and squaring it and adding 1, and the input that we're taking is this 3x plus 1. So we're going to put the 3x plus 1 right in there. I've got 3x plus 1 squared plus 1. Now we're going to simplify this. We're going to square this properly. It's not 9x squared plus 1. Please, people, we're in pre-calculus 12. So it is 9x squared plus 2 times 3x, so that is 6x plus 1, and then we're going to add another 1. So that gives us 9x squared plus 6x plus 2. Okay, and just for those of you who maybe need a little refresher from Math 10, this is a little Math 10 thing here. We got 3x plus 1 squared is actually 3x plus 1 times 3x plus 1. So we have to expand the brackets and use all of my numbers. So we get 9x squared plus 3x plus 3x plus 1. So that's where we get that 6x from. Okay? So one thing to notice, so we actually found this new equation, 9x squared plus 6x plus 2. Two things to notice. Okay? So thing A to notice is 4x equals 3. Let's plug it in and see if we get the same thing we got for the first example, which we should, because if we're composing the two functions, they should work. Our composition of functions should work for every value of x we put in. So we would get f composed with g of x is equal to 9 times 3 squared plus 6 times 3 plus 2. 3 squared is 9. 9 times 9 is 81. So I get 81 plus 18 plus 2. And when I add those up, I get 101. So thing number A to notice is that when I plug in x equals 3, if I do f composed with g of x, I get the same answer, which I should. Part B, notice that for discrete values of x, the method of example 1 is faster. So if I'm actually trying to find, if I'm given what my x value is and I want to find the composition of functions, it's often easier just to plug the number into the first function, then take your answer and plug it into the second function, as opposed to actually finding the composed function and then plugging in your number. Okay, next example. Hopefully that gives you an idea about how we compose functions when we're plugging in a discrete value, just a specific value of x, or when we're doing it for the entire function. Okay, we are going to find g composed with f of x and its domain. And we're going to talk a little bit about how the domain of a composition of functions works. And the functions we're going to be using are f of x equals radical x plus 1, and g of x equals 1 over x minus 1. Okay? So let's start by finding our composition. That's the first thing we're asked to do. It's probably the first thing we should do. So g composed with f of x. So here notice the f is closer to the x, so that's the function we'll be applying first. That's equal to g of f of x. Okay, replacing our f of x with what f of x is equal to, that's g of radical x plus 1. And now g is 1 over x minus 1, so I'm going to be replacing the x in 1 over x minus 1 with the output for my x function. So this is going to be 1 over, and that's where my x was, minus 1. So I'm going to plug in radical x plus 1 minus 1. Okay? So my domain, I have to look at my domain now. So first of all, I have this f of x. So I'm going to be plugging something in, and I can't plug something into a function if it doesn't exist. So I know that my domain is going to be restricted to whatever the domain of f of x is. Okay? So let's take a look here. Okay? So for f of x, okay, we have radical x plus 1. We're taking the radical refers to the square root. We know that roots with even indices can't have negatives underneath them. So the input here has to be positive. But it's not the x that has to be positive, it's actually the x plus 1, because if I had x had like x equals negative 1/2, negative 1/2 plus 1 is positive, so that's okay. Okay, so this piece right here can't be negative. We'll talk a little bit more about this when we get to our chapter 4, which involves radicals. So now we got x plus 1 is greater than or equal to 0, just saying. So that inequality is really just saying this has to be positive or 0. we can solve the inequality just like we would solve an equality, and we get x is greater than or equal to minus 1. And so that is one of the restrictions we have on our domain, is that x has to be greater than or equal to minus 1. Otherwise, we have a non-real number in that from coming out of that radical expression. So now the other place we have to look, we don't actually have to look at g of x. If we looked at g of x, we would look and say, oh, x can't be 1. But here's the thing. We don't really care when x is 1 because we've plugged in, we've replaced x with radical x plus 1. What we care is when is radical x plus 1 equal to 1. Okay? So for so for our composition of functions, we've already taken care of the piece when is the radical going to be existing. Now we have to see when we have a fraction, so we have to check to make sure that the denominator is not 0. So that's our piece for the composition, is that we now have added a fraction. That layer of complexity requires denominator not 0. So we have radical x plus 1 minus 1. And that's the whole, that's the whole denominator of my fraction. Okay, we know that that can't be equal to 0. So that means radical x plus 1 is not allowed to be 1. And that means the only thing there, and we'll talk again when we get to the radical units more about how to solve this, but we can look pretty clearly and see the only number that's going to make what's on the left-hand side equal to 1 is 0. So we know here that x cannot be 0. Oops. So x cannot be equal to 0. So now what I'm going to do is I'm going to formally write out what my domain is. Okay, and my domain, based on what I see, is x is an element of the set of real numbers, such that, that line, remember, meaning such that, x is greater than or equal to negative 1, and x not equal to 0. And that is the formal domain for this function that is created by composing these two other functions. Okay? Remember, it's sometimes easy to mistake composition for multiplication. When we write a product of functions, we'll be writing g of x times f of x, or g times f of x. The circle has an open kind of a little hole inside, so just make sure you're clear about the difference between g times f versus g composed with f. Okay, last example, and this is one that when you do calculus is going to become super important. So if we can compose functions, sometimes we're going to want to decompose them. So let's find h of x and j of x. So this time we're not looking for a composition, we're actually looking for two individual functions, such that h composed with j of x equals 3 over radical x plus 1, and h of x isn't equal to just x, and j of x isn't equal to just x. So basically saying that we can't have a trivial solution where we say, okay, one of the functions is the whole thing and the other function is just equal to x, so it's just leaving it alone. So we want something a little more interesting. So what we're trying to do when we're finding this is we have our h of j of x. We're really trying to look at our good old friend order of operations. So we want to sort of know within this function what happened first, and that's our j of x, and what happened after. So really what we're doing is we had an x, we did some stuff to it, we want to know what order that happened in. So if I look at this function, I can actually see, so I took the x, order of operations, if I started with x, the radical covers both the x and the plus 1, so it looks like, and radicals have the same order of operations position as exponents because they are inverses of exponents. Again, something we'll talk about a little later in the course. But we have the radical covering both the x and the 1, so that means x plus 1 happened before the radical. Okay, so one way I could break this down, and this is not the only right answer, is that j of x is x plus 1, and h of x is 3 over radical x. So the very first thing that happened was the x plus 1. Okay? And how do I know that works? Well, if I can check it by just taking h of j of x. So if I do if I put the j of x, this x plus 1, in instead of the x, I get exactly what I want. So this is h of j of x equals 3 over radical x plus 1. And you can always just compose the functions to check these kind of problems. So we can also do, let's see if there was perhaps a different way we could do that. So we're trying to get 3 over radical x plus 1. I could have made j of x equal to, well, when we have a fraction, we can see the denominator goes over that whole radical. So it looks like we did the radical before we did 3 divided by it. So j of x could be radical x plus 1, and h of x, my thing that happened second, is going to be 3 over x. Could we do something else? Well, there's almost infinite ways we could do this. We also could have done j of x equals 1 over radical x plus 1. So do everything, do the division, do the radical and stuff, and just forget about the 3. And then have the second thing we do, just multiply our answer by 3, because that would multiply the numerator and give us the 3 in the numerator that we want. So there's a number of different ways you can decompose compositions of functions, as long as you're looking carefully to make sure that your order, what would not be correct is if we had something that was happening in the wrong order. The j of x must be the thing that one of the things that happened first, and the h of x must be what happens after to give you the function that you are looking for.